So here are the rules that I hope you stumbled upon and hope that you were able to generalize. So if you're told the drawing is a whole, what you have to do then is to divide the diagram up into that number of pieces, right? Into 3 pieces. Or I could divide the diagram up into some multiple of 3, because this was probably too hard to divide into 3 perfect pieces, but I bet you divided it up into 6 pieces. Okay, so we can use some multiple of the denominator as long as we then shade, so we divide up into the denominator number of pieces and then we shade the numerator. All right, so this was probably the easiest case. Or I shade the numerator times that constant number of pieces. All right, so when I wrote my rule, I said break the diagram up into b pieces, the denominator, or I had said take the denominator, multiply it. That would be fine. Break it into, you know, in this case, 6 pieces, but then I have to take the numerator and then multiply that by the same constant, and then that tells me how many of those pieces to shade. Okay, the next scenario, which is actually what we were working with on the last page when we did a few examples together, we were looking at cases where the drawing was the fraction. All right, and if it was a proper fraction, and we realized instead of dividing up into b pieces, like we would do if the drawing equaled a whole, right, we had to divide up into a pieces. Again, I could divide up into some multiple of a pieces as well. That would be fine. So if we came down here, I would have divided this up into 3 pieces, and then the way that I decide, I'm sure you would recognize then each of these pieces is a quarter, and so then I would need 1 more quarter to complete the whole. All right, in the example down below, I have 9 pieces, right? So I could say, well, I could divide this up into 9 pieces, and then how would I determine how many more pieces that I need? What I generalized in my rule here is that I would need b times n minus a times n. So I would need 16 minus, I'm sorry, that's not 16, that's 12. 12 minus 9, right? The denominator is 12, the numerator is 9, right? So I would need to add 3 more pieces here to complete the whole. Okay, so 1, 2, 3. Or I could have just looked at this like I divided this up into 3 pieces, right? Each one of these pieces now represents the quarter. Okay, if I have an improper fraction, I want to divide again up into the numerator number of pieces. So here, I want to take this and divide it into 4 pieces, right? If this is 4/3, then each trapezoid represents a third, right? So each of these trapezoids is a third, right? And I see 4 of them. Therefore, to sketch a whole, I would need 1 trapezoid and then another half. Right? That would represent the whole because there would be 3/3. Or in this case, there's 16. So I could say, well, if there's 16 of these pieces, then 12 of them would represent the whole. Okay? Or in other words, break the 16 up into 4. So that would be a third, that would be a third, that would be a third, and this would be a third. Okay, and then I'd want to eliminate that last third. So the whole would be the 12 pieces. So let's see if I want to do any more together. I think I'm going to let you work on these on your own, and then there's some similar problems to this on the collected 5. And let's go to this together. I love these problems, and students don't love them. Right? I love these problems because they're a great way of helping students recognize, what's the whole, right? And how the whole determines the fraction. Okay, so if I say Nate raised blank as much as Tyler, then Tyler's amount is considered the whole. Okay, because we're comparing to Tyler. All right, so Nate would have raised, and no one has trouble with this, 2/3 as much as Tyler. Okay, so the whole for this fraction is Tyler's amount, which is the 3 bars. I'm not going to try to write it here. But now, if I say Tyler raised blank as much as Nate, okay, Nate becomes the whole because I'm going to compare to Nate. So this is a whole. Okay, so when Tyler was the whole, each box represented a third, right? Each box was a third. But if I change the whole, now each box represents a half, right? So then if I say, okay, well then what's Tyler's amount, right? If each square, or rectangle, I guess it is, represents a half, then Tyler has 3 halves. In other words, Tyler would have a whole of Nate plus another half. So Tyler would have raised 1.5 as much as Nate. So I know some of you are not liking this, right? I understand that. This is much more abstract. Okay. So let's try looking at, actually, I'm going to leave 2 for you to try on your own. With the make up your own example, I'm going to give you one. All right, so I'm going to say, Bill ate 3/4 as much pizza as Jane. Okay, then I'm going to ask you to determine, then, oops, I'm sorry, if we compare back to Jane. So we're going to come over here and say, Jane ate how much times as much pizza as Bill? Okay, so Bill ate 3/4 as much pizza as Jane. So let's let Jane's amount of pizza be the whole. Okay, so in this case, Bill eats this much pizza. Okay, so I'm going to put a B. B, B, B. Okay, but now over here, if I say, well, then Bill is the whole. Here, Jane was the whole. Bill is the whole. Right, so this is my whole. And Jane ate 4 pieces when Bill ate 3. Okay, so there's Jane, right? So Jane eats 4 pieces when Bill eats 3. So now this in red is the whole. What did Jane eat? What fraction is Jane if now these 3 pieces are the whole? Okay, and try to fill that in. All right, and if you said 1 1/3, you are correct. Okay, so again, this is another way of making that point. Fractions are always relative to what is the whole. All right, so you go back and try number 2.